Hello, dear parents. Welcome to the second webinar in the series Curriculum at NIS. I'm Ms. Priyanka Lad, the subject head for computer science, and I'll walk you through the curriculum framework of digital literacy subject in middle school and the pedagogical approaches we take to effectively teach this subject. Digital literacy is an exciting and rapidly evolving subject. It has become an ever growing part of human life, affecting many aspects of a person's day. The technology department at NIS aims to develop the mindset of a computer scientist through equipping students with the skills to participate in a rapidly changing world. The curriculum journey incorporates challenging and engaging topics, giving students the opportunity to develop their capabilities, creativity, and subject knowledge. The curriculum has been designed to ensure learners have sufficient knowledge to stay safe online and use computers safely in life. We want students to not only understand how to use technology effectively, safely, responsibly, but also how technology is developed and constantly redeveloped into new and exciting tools. The Key Stage 3 curriculum provides challenges and new experiences in computing, digital literacy, and digital media, regardless of their prior knowledge of using computers, and is designed to ensure students studying IGCSE, ICT, or Com Science have a basis of knowledge, skills, and understanding in the fundamental concepts that are covered in KS3. Over time, students learn and develop proficiency in programming three languages, starting with block based languages before progressing to high level languages. All of the on screen programming activities in the Cambridge Lower Secondary Computing curriculum can be delivered using the Python programming language. It is important for learners to be aware that computer scientists have a number of programming languages options available to them. So learners need to be equipped with the knowledge that underpins them all, rather than becoming technically excellent in one specific language. The curriculum journey connects to other curriculum areas holistically to ensure learning contexts are authentic, meaningful, and provide opportunities for application of skills, investigation, and purposeful play. In addition, references to key events and developments through the history of technology using role models from all aspects of society are used in an inspirational and motivational way for students. So, we have revised the technology learning area to strengthen the positioning of digital technologies in the curriculum. The goal of this change is to ensure that all learners have the opportunity to become digitally capable individuals. This change signals the need for greater focus on our students building their skills so that they can be innovative creators of digital solutions, moving beyond solely being users and consumers of digital technologies. The school will be expected to fully integrate the revised learning area into their curriculum by the start of the 2022 school year. So we have divided the learning objectives into five main areas called the strands, which run through every lower secondary and primary stage. The strands work together to create a holistic approach to teaching and learning of computing skills. The strands are listed in the following diagram. The key stages, which are there in primary, secondary education, are as follows. The transition from primary to secondary school typically takes place at the start of Key Stage 3, and study during Key Stage 4 leads to the IGCSE examination. For demonstration purpose, we'll be elaborating on how the concepts in computing strand progress through Key Stage 3 in middle school. So grades 6 to 8 constitute Key Stage 3 level. Learners should by now have a fair grounding in the techniques of framing algorithms. They are now introduced to a new form of algorithm representation, that is flowcharts. At the introductory level, they are made to follow and understand algorithms that are presented as flowcharts. This helps them gain familiarity with the symbols used in flowcharts, which are limited to start, stop, process, procedures, subroutines, decisions, and connectors. After a certain level of proficiency is achieved, as a step forward, they know they now try to predict the outcomes of flowcharts. The algorithms are made efficient and concise by using same variables and subroutines multiple times in same or in different algorithms. They construct algorithms that can include two or more variables that can be manipulated using arithmetic operators like plus, minus, multiplication, division. They learn to identify the purpose of the algorithm by explaining the use of constructs in programming, including sequence, selection, and iteration. So different types of loops are used to repeat instructions in multiple ways depending on the situation. Procedures and subroutines are introduced through block-based programs to define commonly used sections of code. So they develop application programs where multiple algorithms interrelate using data types such as including integers or characters and strings. Once they learn to identify these data types, they develop text-based programs using string manipulation, including length, uppercase, and lowercase. So, through exposure to an array of applications, they learn that there are many different programming environments, such as block based and text based, and that some are more appropriate to use in a given situation. So, before developing a complete working model, they are made to understand the role of prototypes when designing programs. These could include interfaces for programs, including suitable prompts for its users. Programs are evaluated against a set criterion and tested using a range of data. Eventually, testing becomes a deliberate process that is more iterative, systematic, and proactive. So they develop programs for physical computing devices to generate outputs based on a range of inputs, including the use of variables. Grade 6 explores the role of hardware platforms in computing and how different sensors can provide more effective input and output than traditional keyboards, mouse, and monitor. Using microbit, they develop circuit programs that utilize same hardware inputs and outputs that you see in smart devices, and looking at how a simple rough prototype can lead to a finished product. Alternatively, learners could design a game controller using Makey Makey and conductive materials such as tinfoil. Uh, then they can work out which blocks in Scratch they will use with their controller. The topic gradually progresses to memory size and storage unit, in which they learn to identify what are nibbles, what are bytes, what are bits, and other storage units, how to convert between storage units, the internal architecture of a computer, that is, role of a processor, primary memory, and secondary storage, and the relationship between them is studied. Through augmented reality, that is AR, we as educators are able to improve learning outcomes through increased engagement and interactivity. With a mobile device or tablet, students can use AR apps to access projection based, location based, or recognition based experiences so that objects, artifacts, or media appear to be in the room. Students are then able to interact with the content by moving around, getting closer to it, and manipulating it to research and learn more about it. In grade 7, they learn to differentiate between VR and AR technologies and identify the use of augmented reality in familiar contexts, including education and entertainment. By grade 7, they know how to create algorithms using flowchart symbols and to follow and understand the logic of and or not operators. How relational operators are affected by negation, that is, let's say, for example, not A greater than B. This could be something that they learn in this grade. They understand and use selection statements limited to if, then, else, which are presented as flowcharts. They can now predict the outcome of flowcharts that use selection. Compound conditionals combine two or more conditions in a logical relationship, and nesting conditionals within one another allows the result of one condition to lead to another being evaluated. So learners will experience using multiple uh, and mixed structures, such as combining multiple loops to draw a spirograph, as you see on your screen. Spirographs shapes or multiple conditions, for example, creating a rock, paper, scissor program on a microbit. They should have an opportunity to try more complex conditional statements, such as repeat while not finished, or if touching red line but not positioned at the edge of the stage. This is how they learn to combine complex conditions in one program. In web languages, advanced learners will be more confident at HTML and CSS and trying to add interactivity to their pages using simple lines of JavaScript. For examples, learners could use mouse over and mouse out JavaScript attributes within an HTML tag to allow the color to change when a mouse is moved over and then away from a piece of text. So, alongside programming, documentation of processes, is parallelly followed. They learn to document what they are programming, what steps they have taken. Project plans are developed with details on test data. Documenting programs to explain how they work. Tracing the control flow in a program gives them an exposure to understand how and what types of errors can be introduced into programs. A systematic approach is taken to identify and debug errors in text based programs. They can identify a range of errors, including syntax, logic, and runtime errors, and find and correct them. They use trace tables to systematically debug text based programs. The testing of an algorithm requires the use of inputs that reflect all possible conditions to evaluate its accuracy and robustness. So, as students progress, they should become more adept at debugging programs and begin to consider logical errors, cases in which a program works but not as desired. In this way, students will examine and correct their own thinking. A single program may be solved by several different algorithms. The choice of an algorithm to solve a problem at this age level should be driven by what is required of the solution, such as the code complexity, speed, amount of memory used, amount of data, the data source, and the outputs required. So students learn to make these considerations while coding, along with the need for accuracy of both algorithms and data, that is data validation methods. So they compare and contrast algorithm designs for the same task to determine which is best suited to the purpose. Eventually, students should include more factors in their evaluations, such as how efficiency affects feasibility, or whether a proposed approach raises some kind of ethical concerns. So, with a substantial experience in computational thinking and problem solving, grade 7 students are now ready to take on broader social impacts of computing through a series of design challenges to better understand the needs of others while developing a solution to a problem. So they work on an iterative team project of app development, during which teams have the opportunity to identify a need that they care about. Could be prototype solutions in MIT Lab Inventor or App Lab, and test solutions with real users to get feedback and drive further iteration. This is an opportunity for students to explore other roles in software development, such as project management, or let's say marketing, design, testing. So far, up to grade 7, uh, we have been working with structural and procedural aspects of Python programming. To take it a step further, students write code to import modules in Python. So modules are these pre-installed Python libraries, which are runnable codes that allow users to import functionality from those codes to remix and create something of their own. So students have fun experimenting with the methods and functions in it, while creating mini games and animations. Python GUI library has been gaining a lot of interest recently. Students create nice looking interfaces with programs that help users interact with application. As a base to computer fundamentals that they would be learning at IGCSE level, binary number system is introduced in grade 8. It is a fun exploration for them to see how binary numbers can represent different data such as numbers, characters, images, and sounds, how analog images and sound can be digitized. ASCII is used to represent characters. Basic conversion from binary to denary and denary to binary is taught as a precursor to data representation unit in ComScience IGCSE. The role of DAC and ADC is impressed upon students through various examples. While science hasn't quite delivered those sci-fi dreams, the emergence of AI has definitely arrived and left us wondering what now. Our philosophy at NIS is to empower learners with the skills and knowledge to make AI technology solutions that also respect users by reflecting on empathy and ethical concerns of AI development. We do this by providing students with real AI software driven platforms to work in a guided projects that teach students how to, for example, install Python libraries for natural language processing, or how to set up an AI system that can make predictive sounds with a drum machine. In middle school, we focus on innovative ways to introduce students to the fundamentals and applications of AI. Our first objective is that everyone needs to be able to recognize AI and its influence on people and systems and be proactive as a user. Second, everyone should have the opportunity to use AI and big data to solve problems. And third, young people interested in computer science as a career should have a pathway for building AI. AI applications can impact society in both positive and negative ways. Emerging issues such as, that include the use, the fairness, and transparency of algorithms, and likely social impacts are discussed at grade 8 level. We strongly feel that adding the ethical implication and empathy of understanding how AI is being used is vital to prepare students for the not so distant future of advanced AI. This is a message that we purposefully weave into our curriculum because we value the teaching of empathy as a critical skill needed to prepare conscious global citizens who will be charged with building the future while using technologies like AI. So Python has been the go-to choice for machine learning and artificial intelligence, developers for a long time, and hence we have been training users in the language since grade 6. So using PictoBlock's AI curriculum, in AI curriculum, students are taught AI and machine learning in an interactive and playful manner through engaging, AI projects such as identifying celebrities in an image, making a face detector, recognizing handwritten and printed text, building machine learning models, and some other projects, which are quite engaging for students of this age. So AI concepts or techniques such as computer vision, face recognition, text recognition, natural language processing, and speech recognition are covered through hands-on AI projects in PictoBlocks. The third section of the AI curriculum for schools, introduces students to machine learning and how to make ML-based projects such as post classifier and an AI version of rock paper scissors game. The fourth section of AI curriculum introduces students to ethics and why they are important to keep in mind when learning and applying concepts of AI and machine learning to their projects. The final section of the AI curriculum is where students get to apply all the concepts that they have learned in the previous sections to make a capstone project to solve a real world problem of their choice. Students also conduct Google AI experiments and create machine learning projects using Google Teachables machine platform. Along with that, we discuss big ideas in AI like automation, what makes a system or process function automatically, and design and manufacturing of robots. So they study application of automation in at least two industries such as health, manufacturing, advertisements, or gaming. So we also give learners opportunity, to take up field trips, that are arranged. For example, exposure to how cloud computing, sensors, machine learning, and hardware is used to automate the Amazon delivery process and maintain stock data in their database. So robotics is hands-on and offer exposure to mechanical design, electronics and programming, all of which are critical STEM skills. By teaching robotics at middle school level, it is possible to attract and maintain student interest in STEM fields. Students create small, customizable, programmable robots using software and hardware that comes with a series of kits called Lego Mindstorm. They include an intelligent brick computer that controls the system, a set of modular sensors and motors, and various Lego parts to create the mechanical systems. By the end of Key Stage 3, students can combine multiple constructs such as sequence, um, selection, counter control iteration to write algorithms as flowcharts or pseudocode using iterative development on software prototypes to produce solutions to problems. They develop and apply test plans that include normal, extreme, and invalid data. The choice of an algorithm at this stage is influenced by the data structure and data values that need to be manipulated. So students discuss the purpose of selection of data structures and evaluate their use in terms of trade-offs between performance and storage requirements and their suitability for different algorithms. They develop an understanding that different algorithms may have different performance characteristics for the same task. So let's have a look at the approaches we take to teaching digital literacy in middle school. In middle school years, we encourage students to play with, explore, and experiment with the essential idea of taking something and seeing how it works. Of tinkering with it, um, of adapting something to new purpose, and at its heart it is a creative discipline. We make things, we learn best through making things. We learn so much through testing things, through fixing things when they are not working. And there's this popular statistics that programming is just 20% writing code and 80% fixing code. So debugging is going to be such an important part of this, and you learn so much through those situations where it doesn't work as you expect, and coding is the new gaming that we learn, through which we learn about persevering. So our approaches are underpinned by our principles of computing pedagogy. As you can see on the screen, these are the themes that you would find, running through all of the units that we cover, or all of the concepts that we try to incorporate in computing strand of our subject. So, learners need support in acquisition of knowledge through the use of key concepts, terms, and vocabulary, providing opportunities to build a shared and consistent understanding. Glossaries, concept maps, and displays, along with regular recall and revision, can support this approach. So determine the list of concepts, ideas, or keywords that are relevant to the focus question. If it makes sense, order them according to how general they are or how relevant they are to the focus question. This is the first step towards structuring the concept into hierarchy. The process of constructing a concept map, and even that of reading and interpreting it, is demonstrated by us, the educators. Building a concept map can be a collaborative task even. The second pedagogical approach that I would like to elaborate on is how we give opportunities to learners to work collaboratively. So, collaboration specifically using pair programming and pair instruction and also structured group tasks are quite effective pedagogical approaches to teaching algorithmic thinking. So, working together stimulates classroom dialogue, articulation of concepts, and development of shared understanding. Pair programming is a pedagogical approach which involves learners working together on a problem to develop programs. Learners take turns playing the role of the driver and the navigator, swapping roles at intervals. This will make sure that everyone is playing an equal and active role, and they are encouraged to think in different ways, and both the learners take ownership of the problem that they are solving. Peer instruction relies on carefully selected MCQs based on some pre instruction material. In class, the MCQs are combined with peer discussion to explore and challenge students' understanding. Crucially, peer instruction begins with some form of pre instruction like reading, videos, etc., where learners can study and become familiar with the material in question before the discussion is held. This is also commonly called as a flipped classroom approach. Another approach that we get is to, get hands-on. Physical computing and making activities offer tactile and sensory experiences to enhance learning. Combining electronics and programming with arts and crafts, especially through exploratory projects, provides pupils, with a creative and engaging context to explore and apply computing concepts. Physical computing is a broad term to describe activities where learners write programs to interact with real world using specialist hardware. While there are many examples of physical computing devices, they are typically able to do a combination of some or all of the following that we are going to explain. Control a simple output component such as lights and buzzers, measure or record the environment in some way, including through sensors, buttons, and switches, drive and control motors to create movement. When considering what devices to work with, we as facilitators review the features, connection methods, and means of programming, as well as the flexibility that each device provides. I'm going to elaborate on another pedagogical approach we take, that is unplug, unpack, and repack. So, new concepts are introduced by first unpacking complex terms and ideas, exploring these ideas in unplugged and familiar contexts, then repacking this new understanding into the original concept. So, learners can explore different simple encryption methods such as scissor cipher, pick pen, Morse code, perhaps using a murder mystery theme, such as the one shown, in the image. So we give them, a task which is a mystery solving task, and they have to figure out, the answer to the task by solving certain ciphers that are involved in it. Compression is taught in an unplugged way, such as activities from CS Unplugged site. Learners could find out more about the Enigma machine and the history of Bletchley Park. Learners could race to sort and search for information using different algorithms. There are many unplugged activities for teaching sorting networks where students need to follow a simple algorithm and each node compares two values. So, unplugged activities for searching could also include algorithms wherein you ask 20 questions, and they have to come up with intelligent questions to arrive at an answer. And the responders can also only respond using a yes or no as their response, just one word response. In class, in the classroom, learners could learn how to use an ASCII conversion table to show their names in binary, perhaps even representing the binary as a bracelet using different colored beads. Learners could use an unplugged activity to create simple black and white binary images and convert them into binary code. After exploring simple encryption methods such as scissor cipher, PicPen, Morse code, learners can then discuss how easy these are to break now, and the methods used currently, such as public and private keys. This could be done using an unplugged activity on public key encryption. Towards the end of KS3, learners can write code which receives and responds to real world inputs in a visual language. Learners could use microbit to create dice or rock, paper, scissors games. They could create papercraft characters for microbit and then program the device to display different faces depending on whether it is lying down, upside down, or being shaken. Microbit could be programmed to do different things depending on messages from another microbit device using radio commands. There are a number of ways to use Scratch with alternative inputs. Team of learners could work together to create a game and make a game controller using Makey Makey device or Lego Video sensors to control the game. The latest version of Scratch allows learners to easily use a webcam to control sprites using motion detected on camera. Learners are made to think about the information and processes that might be involved in real life systems they see around. For example, in growing vegetables and how these processes could be automated. They could watch a video of the FarmBot automated systems for gardening and could then identify the steps in the processes required to plant, maintain, and harvest crops, and then investigate the sensors used or data required to allow each of the stages to be completed by a computer system. Think about how AI could be used to identify the difference between a weed and a crop, or work out if watering is required or if the crops are in good health. Um, there could be a discussion on how self driving cars navigate, choosing an efficient and safe route, avoiding obstacles, redirecting based on traffic reports received in real time, choosing a route, avoiding roadworks based on crowdsourced information. Students can consider, uh, the moral dilemmas in crash situations through discussions and using a quiz and discuss how their views compare to other learners and to the average on a website where you could have such simulations. Learners could race to find an item such as a name in a phone book or a word in a dictionary and compare the speed of different approaches. Learners could do a similar exercise with sorting algorithms as well. Discuss two or three different sorting algorithms such as quick sort, bubble sort, and insertion sort, and compare number of number comparisons that occur in an algorithm, number of swaps that take place, memory requirements, and overall time taken. When transitioning from visual block based programs to textual instructions, learners could create a dictionary matching visual language block commands to their textual language equivalent. Ideally, this should also include a definition of each command written by the learner. This dictionary can be started with a basic set of commands and then developed gradually by learners as they come across new commands. They could then use this dictionary when creating programs for their capstone project at the end of each grade. As a step further, learners could be given specifications for a number of hardware systems that would run programs using sort or search algorithms. They could make recommendations based on their knowledge of speed, process, complexity, and storage requirements to rule out unsuitable algorithms for a particular system. Learners should be able to create and manipulate strings and arrays in a textual language. Learners could manipulate text in fun ways, such as using substring commands in order to select parts of strings, such as generating Star War names, which consist of first three letters of your first name, first two letters of your surname, and three letters from your mother's maiden name, and two letters from your own birth or birth town. This is also a great opportunity to discuss fishing with learners. So learners could use dice to randomly choose values from arrays in order to create a nonsense sentence or haiku. Learners could work in groups to research a technology that they have chosen from a list. They can find out how it was developed, why it was originally created, and the basics of how it works. They could then produce a poster, give a presentation, or just make a video, animation, or web page on their chosen technology. Computing and especially programming is a subject with lots of technical terms that have precise technical meanings. To succeed, learners have to master the terminology whilst simultaneously developing a firm understanding of the concepts. A great strategy to support learners is to make learning experiences follow a semantic wave. This involves introducing abstract concepts with the associated terminology, but then using simpler language to explain their meaning. This is why metaphors, analogies, and unplugged computing are powerful ways to teach. However, it is important to then help students link those simpler meanings directly back to the abstract concepts and associated technical language. For example, when educators introduces the idea of variables and assignment using technical words and abstract concepts, learners are at the top of the semantic wave. To help learners descend the semantic wave, the educator might explain variables using boxes. To help them descend further, the educator might then illustrate explanation with physical props. However, the educator shouldn't leave learners thinking that it is just about boxes by only talking about moving values between boxes. They must help learners link it back to the technical and abstract so that learners can surf off back the semantic wave. The next thing that we do is model processes and practices. Everything from debugging code to binary number conversion, using techniques such as worked examples and live coding. Modeling is particularly beneficial to novices, providing scaffolding that can be gradually taken away. Worked examples demonstrate an expert solution to a problem and are used in many subjects to support novices who use the examples as as blueprints for solving new but related problems. Another aspect that I would like to elaborate on is live coding. So when learners read static completed programs, they aren't exposed to the troubleshooting that has already taken place to get to that end product. This is known as being product focused. Live coding is when a teacher develops the solution to a problem in front of the class for learners to follow, which is known as being process focused. So novice programmers can often look at a finished program and have the misconception that it has been written from top to bottom and that a skilled programmer always knows exactly what they are doing and can just write out what they need without making any mistakes. As any programmer or even a writer knows, this is not the case. Live coding demonstrates to learners the incremental nature of programming. It shows that problems are decomposed into small sections that are programmed, tested, debugged before the next stage is worked upon. When live coding, we plan intentional mistakes. Intentional mistakes are linked to common errors or learner misconceptions in order to target and alleviate them. A learner can also verbalize teachers' thought process so that the class can see what they should be thinking when they come to do the same thing. There is this platform called Replit, which provides collaborative live coding experience to students from the browser. It provides Google Doc like editing experience where you can see your collaborators' cursors. Learners can run code and see the same results together. A variety of activities are used to consolidate knowledge and understanding of the function and structure of programs, including debugging, tracing, and Parsons problems. The activities are devised to develop comprehension in each of these 12 zones in order to support learners' full understanding of the program. A simple strategy that works at all levels of focus is to identify aspects of the code within the text. By identifying examples of variables, conditions, finite loops, functions, etc., we help learners make sense of the text and connect it to the underlying concepts. During program execution, several approaches could be used to help learners develop their understanding and their mental models. For example, learners could trace simple programs determining the end state of variables, or the inputs required to reach a specific state. Similarly, learners could investigate the effect of swapping two lines of code or try to find lines that never run. Learners can also benefit from exploring functions. Asking learners to explain the function of a line, snippet, or entire program is a great place to start. To do this, they will have to use clues within the text and observe the execution. Also, the function can be connected back to the text by asking learners to provide meaningful names for variables or functions or entire programs. Alternatively, learners could be given a description of the purpose, um, and made to identify a program that matches, or compare multiple programs to find which are functionally equivalent to what we have provided. Use formative questioning to uncover misconceptions, and adapt teaching to address them as they occur is what we generally follow. Awareness of common misconceptions alongside discussions, concept mapping, peer instruction, or simple quizzes can help identify areas of confusion. Abstract concepts are brought to life with real world and contextual examples, and a focus on interdependencies with other curriculum subjects. This can be achieved through the use of unplugged activities, proposing analogies, storytelling around concepts, and finding examples of the concepts in learners' lives. Supportive frameworks are used when planning lessons, such as Prim. Prim stands for Predict, Run, Investigate, Modify, and Make. PRIMM. And there is another model we follow, that is Use, Modify, Create. These frameworks are based on research and ensure that differentiation can be built in at various stages of the lesson. Let me elaborate what Prim approach is. Prim stands for Predict, Run, Investigate, Modify, and Make, representing different stages of a lesson or series of lessons. Prim promotes discussion between learners about how programs work and the use of starter programs to encourage the reading of code before writing. The five stages of Prim, as you can see, the first one is predict. Students discuss a program and predict what it might do. They can draw or write out what they think will be the output. At this level, the focus is on the function of the code. This works well as a pair activity where learners can discuss their predictions and practice their use of computing vocabulary. Students run the program so that they can test their predictions and discuss in class. This is what happens in the run stage. In Investigate, the teacher provides a range of activities to explore the structure of the code, such as tracing, explaining, annotating, debugging, etc. The Investigate phase of Prim gives us the opportunity to devise creative activities and ask insightful questions about a program. In this way, we are moving from thinking about what the code does to how it does it. In Investigate phase, we often use a range of activities. Here are some examples. So let's say we could ask them questions like, what would happen if these two lines were the other way around? Or what would happen if the input to the program was XYZ? Or we can ask students to draw on the program to identify blocks of code or type of construct. Draw the flow of control on the program, showing what line is executed when a loop is exited. Ask students to identify the scope of a variable. Identify the purpose of a single statement. These activities can be varied and added to, and many teachers have been very innovative in how they ask questions of students that really get them thinking. The next stage is modify. So here students edit the program to change its functionality via a sequence of increasingly more challenging exercises. The transfer of ownership, if you observe, moves from the code being not mine to partly mine. And as students gain confidence by extending the function of the code, learners modify the code that they are given and observe how these affects, the output. And that is how they gain ownership. And finally, it becomes, my own code, and something that is original to them. The next stage is make. So students design new program that uses the same structures but solves a new problem, that is has a new function. The focus on language and talk and the use of starter programs draws on a socio-cultural perspective to the way that children learn programming. Learners are given a problem to solve that uses the same constructs and structures that they have just understood so that they can apply their new knowledge to a new concept, to a new context. Encouraging talk in the classroom is what we focus on. Code tracing, well, learners can be better supported to write effective computer programs by focusing on program comprehension. Developing this skill helps them to understand and interpret a program and discern its function. Code tracing supports this development by encouraging learners to read, understand, and record the behavior of a program at different stages of its execution. Learners could also be given short sections of code in the form of worked examples or complete trace tables where some values are provided and learners use code tracing to record the missing values. Project based learning activities provide learners with the opportunity to apply and consolidate their knowledge and understanding. Design is an important, often overlooked aspect of computing. Learners can consider how to develop an artifact for a particular user or function and evaluate it against a set of criteria. It can be helpful to use PBL in the classroom so that learners can apply their existing computing knowledge to new situations and deepen their understanding of programming concepts. Projects usually take place over a number of sessions and will typically be split into several stages. PBL often involves using a mixture of software, hardware, and other physical material. Learners are given repeated opportunities to discuss their work so that they can identify and begin to address their own misconceptions. Lastly, Parsons' problem is something really interesting. So, an important precursor to learning to write computer programs is having the necessary program comprehension to interpret the function and structure of existing programs. One tool that can help learners develop program comprehension is Parsons' problem, uh, which are basically exercises that require learners to rearrange lines of code into correct sequence. A Parsons problem is a task in which learners are given all the blocks or lines of code needed to solve a problem. However, the lines have been jumbled so that they are no longer in correct order. Learners are asked to reorganize the code into the correct order to perform a specific task. So some Parsons problems include distractors. Distractors are incorrect blocks or lines of code that are included in a set of provided code, meaning that learners need to be selective about which block they use. The understanding of what we can and cannot do with computation is arguably the most important intellectual achievement of the past century, and it has led directly to the development of the computational infrastructure that surrounds us. There are many aspects of our life today that would not be possible on the same scale without the use of computers. So, studying what they are, how they work, and the many purposes they have is both fun and exciting for learners. With the digital age rising, there is a need to develop logical thinking and problem solving, which are all a part of the computer science curriculum that we offer at NIS. Our learners don't have to be genius to know how to code. They just need to be determined and resilient. Addition, subtraction, multiplication is probably all what they need to know. With the empathetic approach we take to develop design and computational thinking skills in learners, they realize that coding systems and software programming is really about humanity. There's a lot of social problems right now that could really leverage the use of technology. And that is the outlook, the attitude they develop through this subject. Parallelly, through other digital literacy subject strands, learners investigate wider social ethical issues surrounding technology and their broader applications in industries and varied businesses. Computer science is an evolved branch of mathematics that provides the foundation for all the magnificent achievements of human discovery. exploration, progress, and prosperity that have radically transformed our quality of life and understanding of our universe in mere decades. Whatever the future holds for us, whatever human endeavors await to be undertaken, you can bet computer science will continue to play at center stage. And we want our learners to be active contributors to the digital world. With that thought, I conclude the webinar. Thank you. I'm signing off from here. This is Priyanka Lad, the head of Computer Science Department. If you have any queries, please do reach out to me on priyanka.lad@nahar-is.ac.in. Thank you so much.